In this video, we're asked to compute the area bounded between y equals x squared and y equals cosine x. So let's look at the graph real quick and figure out which one is which. Well, y equals x squared is an upward facing parabola, so it must be this one, passing through the origin as well. And so the other one must be the cosine function, just this yellow curve. And interestingly, we're told in the problem you will have to use a numerical approximation for the intersections of the curves. And the issue there is that if we algebraically search for these intersections, we would set the two y values equal to each other and ask, what's the value of x when the two y values are equal? And this equation has no analytical solutions. And so what I'm going to do is use the find root function in WX Maxima, as the computer algebra system that I use. And Maxima can't directly tell you what the intersections are between two curves, but it can tell you where the roots are of a function. In other words, where a function is equal to 0. So I transform my equation to this equivalent equation by subtracting cosine x from both sides. And then I'm going to ask Maxima, where is this function equal to 0? And that's the x value of the intersection. And I can see that this intersection on the right side of my picture happens somewhere between 0 and 1. And I don't need to worry about the one on the left because I'm just going to take the right half of the area and double the answer anyway. So here we are in Maxima, and I'm using the find root function, and I put in x squared minus cosine x. And then I have to tell Maxima what interval to search on for a root, so as x goes from 0 to 1. And then I'll hit Shift Enter. And I'm just going to round this to the thousandths place. I get an approximation of 0.824. Next, I'm going to get into setting up my area integral. So I'm going to look at a little area increment, a thin vertical slice of this area. And then the whole idea behind this is that we say as long as we're slicing finely enough, these are very well approximated by rectangles. And the width of each of these rectangles we call dx. And the height is given by the y value of the upper function minus the y value of the lower function, so cosine x minus x squared. Then we refer to this little area as an area increment dA. So I can write dA is given by the height times the width for this little rectangle, cosine x minus x squared dx. Then I use an integral to sum all of those dAs. So that's what integration does. It's a summation device for summing a bunch of continuously changing infinitesimal contributions. And I'm going to go ahead and take, as I'm working here, twice the integral of half of this area. It's a little nicer to do it that way. And at this point, you might argue that I'm using an approximate intersection anyway, so I might as well use a computer to get an approximate result of the integral. But it would be a shame to miss out on guessing the antiderivatives here, so I'm going to do that. So I get twice sine x minus 1/3 x cubed. And this is evaluated from 0 to 0.824. And when I plug in the lower limit, I get the sine of 0 and I get 0 cubed. So none of that is contributing anything. So that's gone. And all I have to do is evaluate 2 times the sine of 0.824 minus 1/3 0.824 cubed. Make sure your calculator is set in radians. And I get 1.09 approximately for the area. The last thing I'd like to do here is take a look at my picture, and the size of the grid squares on there is 1. So this is y equals 1 right here, x equals 1 right here, and that means this square on the right hand side has an area of exactly 1. So I'm just looking for the reasonableness of my answer. Can I say that the total area bounded between these two curves, if I put it all together as close as I could to a square, would it be just a little bigger than one of those squares? And it looks plausible to me, so this is good. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.